So here we see our very first fun and introductory problem to moments in 3D. And what we really see here is a force that is acting at a pipe structure at A with 500 newtons in a random direction that's described by these triangles. And the pipe itself is random in space. And we first have to determine the moment that is acting at O, so that's this point down here, due to that force. And then later on, if we want to, we can calculate the moment at the top of the vertical pipe, which means right here, 003, due to that same force. And I think we can find some interesting revelations once we compare the result from part A to part B. But let's go ahead and look at that problem first. And what do we need, right? So always start out with the formula. We need m about O in this case is a vector which needs to be equal to r cross f. So how do I do that? Remember, I need rx, ry, and rz. So that is one thing I need to find. And I also need to find fx, fy, and fz. So these entities is really the challenging problem here. And I say it again, this is really what mechanics teaches you, how to see that. It's not solving this equation. You learned this in mathematics. I showed it to you on the previous 2 pages, don't get me wrong. But really what we need to learn in mechanics to be successful is how to identify these entities. So let's go ahead and start with R, because I believe that's the easier one. So what is R? It's the moment lever arm from, in this case, the point of origin to point A. Be careful, because the coordinate system is given such that we deal with -2 in the I direction. We deal with +2 in the J direction and +3 in the K direction. And that is in meters in this case. It's important to keep that. Now, how do we find the force? Of course, you learned that in many different examples. Let me zoom in. So the easiest one is probably to calculate this one, which is really nothing else than 500 divided by 5 multiplied by 3. So this is 300, of course, in Newton. All right, now I need to first project it into that plane that is actually parallel to the xy plane. So let's find this component first, this here. So that component is nothing else than 500 divided by 5 multiplied by 4. So that's 400. And now I can further convert it, but be careful. This clearly goes in that direction. Let me also identify in which direction the red component goes. It goes up. But now I can further break it down into, let's say, a blue component, which I may go in this direction. So that would be nothing else than 400 divided by 5, and in this case multiplied by 3. So that, I believe, gives us 240. Be careful, this is negative, right? All right, now that we have that one, we can find our y component, which is in this direction. And I believe that's nothing else than 400 from the first calculation divided by 5 as well, multiplied by 4. And in that case, that turns out to be 320. And of course, all these are in Newton, right? So maybe I should add that here real quick to not get in trouble with my students. All right, now I can describe both in ijk form, and maybe just for completeness reasons I do that real quick. So my r vector I already did. My f vector is really nothing else than the x direction first, right? So an x direction is negative in this case, minus 240 I hat. The y direction is positive with 320 j hat, and the z direction is also positive with 300 k. And that, of course, now is in Newton. And that is really the challenge to these problems for a beginner, right? So solving this is not really difficult. That's just mathematics. Of course, we're going to do that now. But please understand that the art is in these two expressions here. Let's go ahead and convert it to our determinant solution. So let's say that I have R cross F, which is nothing else than I hat, J hat, and K hat. And I have -2, +2, and 3, and -240, +320, and +300. And my bars come in now. And I add my two columns just to make my life easier. -2, +2, -240, and +320. I make my life easy by actually drawing the diagonals. Some think it's a waste of time. I certainly don't. So let's go ahead and add that. So I have this diagonal, I have this diagonal, and I have this diagonal. And now I'm gonna actually, because I have no room on the top, I'm just gonna do it downwards as well. So I have the negative diagonal here, I have another negative diagonal here, and a last diagonal here. Now let's collect the terms. So I have plus, and now +2 times +300. So that is equal to +600. I don't even need a calculator for this problem, as you can see. Now the next one, +3 times -240. So that's 720 if I'm not mistaken. So, but negative -720. And then I have -2 multiplied by 320, which I believe is equal to -640. And technically everything that I calculated here is plus, just to stick with my convention here. This was the I component, this was the J component, and this was the K component. But now I move on to my other side and deal with my negatives here. So maybe I can leave a little bit more room here. Minus +2, so +2 times, what do we have? -240. So that makes the entire expression here positive. So we have +480. And that happens to be the K component, by the way. Now let's go to the next one. We have -3 times +320. And that is equal to -960. And that is that is actually equal to, I hat. And because I don't have room here now, I'm going to use the upwards diagonal here, which is -2, and the whole thing negative as well, times 300. And that means that we're looking at positive 600 J hat. All right, now I can collect all my components. Let's do that one by one. So first, I just write them down as two individual vectors. So for example, I have 600 plus 600 I hat minus 720 J hat minus 640 K hat. Now I need to be a little bit more careful, right? So by the way, I need a plus here, or I guess that should be individual, but I need to be careful because now my signs are all over the place, or my IJK. So I have a negative 960 I hat. I have a plus 600 J hat, and I have a plus 480 K hat. And of course, we already understand that here we have meters, and then here we have newtons. So therefore, my entire expression needs to be in meter Newton, but nobody would ever say that. You, of course, would always say Newton meters. So let's say that. In the British system, that's different. Foot pound or pound foot is both used, but Newton meter is, I think, the convention in the metric system. Now, all I have to do left is to actually find the solution to the combination of these two vectors here. I could have, of course, immediately combined the I components, the j components, and the k components, but what I end up with is definitely a vector in a 3D description. So 600 minus 960 is minus 360 I hat. Then we have minus 720 plus 600 means minus 120 j hat. And we have minus 640 plus 480. So that means we have minus 160. And you see, I don't even need to get my calculator for all this. But now I have Newton meters, and I can pull out my ruler because this is definitely an answer to the question. It's actually one part of the answer, but I definitely need my answer arrow here. And let's think about what this now means. We have minus 360, minus 120, and minus 160. So now we can take this back to our initial diagram here and actually visualize these results. So let me pull out my ruler here and draw the first moment, which, remember, that was negative 360, right? So negative 360 means nothing else than a negative direction, a rotation in the negative direction. So this here was 360. And please note that I used a positive number here because the direction shows negative, right? So we will never draw negative values in a sketch. We only draw positive values in a sketch. And here I drew it with 360 in that direction. Now I also have the y direction, which I believe was given with 120. That would act in this direction. And this is not to scale, of course, but this would be 120. And last but not least, I have a rotation about the z-axis, which was negative 160. So now we have a visual interpretation of our results, and I encourage you to think strongly about this, and then also think strongly about how we actually get our moment magnitude, right? Which in this case is nothing else than 360 squared plus 120 squared plus 160 squared, and then square root it. So if I punch that into my calculator, this is probably where I would need a calculator, but I will end up with 411.8 Newton meter. And that once again is a result. So I now have to use my answer arrow and indicate this properly. And I want you to think for a second about this versus this. You just saw in the diagram what this is. So maybe you can tell me what this is. I give you 2 seconds to think about that. All right, ready, set, go. Let's take a look at this picture here. And it's very difficult to show this on a 2-dimensional piece of paper, or a virtual 2-dimensional piece of paper, but you have these axes here that go down, go back, and go to the left, if you will. So these two here are in the xy plane, and this is in the z direction. And together they kind of form a box, and I will try to draw that box for you, but it will lead to more confusion, probably. But I want to attempt it. So I have, let's say, the top surface of that box that looks like this. And this entire surface is in the xy plane, right? So this is all in xy. And then I also have a depth of that box, which would go down here in the back. And I'm not going to draw the entire box because it would just confuse you, or it would just confuse me, I guess. But I have a top corner here. Let's call this the top front corner. And let's call this the top back corner. Let me draw that in a different color. So I have the top back corner. And now under that top back corner, there's also the bottom back corner, and I'm going to indicate that right here. And there is a vector that actually connects the bottom back corner to the top front corner. And I draw that in red here. So there's a diagonal, which is really difficult to see, but there would be a diagonal that would go in this direction, right? And that would be M magnitude, which we calculated to be 411.8 Newton meters. So again, please understand the physical significance. So this here is at the origin. This black point is below the origin, below by 160, to the back by 360, and to the left or to the y direction by 120. And we're connecting the 2 points of this box with this 411. That's really what that is. So now you have a solid physical interpretation of the moment vectors. So we are almost done with this problem. The last thing we technically have to do is calculate the base vector or unit vector, I should say. So m hat would really be equal to minus 360 divided by 411.8 I hat minus 120 divided by 411.8 j hat minus 160 divided by 411.8 k hat. And that is unitless, and that qualifies as an answer for the direction because it's just the same as the directional cosine. So I'm going to double underline this as well, and of course use my answer arrow. But if I were to calculate actually the cosines, please understand that alpha would be equal to 150 degrees, beta would be equal to 106 degrees, 106.9 I believe, and then gamma would be equal to 112.9 degrees. And that is important to understand when you calculate this, because these are all values that your calculator don't immediately will give you, because we're dealing with the negative directions. So you need to have a physical proper understanding of these angles. We had a whole lecture about this, so I'm not going to repeat that here, but you can tell from the negative, and the negative here that these angles must be larger than 90 degrees, right? And that can be tricky depending on how your calculator spits out your answers, but you already are familiar with that method. However, we are now done with this problem, and I encourage you to think deeply about this and how you would have solved it. The most important thing to begin with for somebody who's just learning mechanics is, can I really convert this physical description into a mathematical description? And I think I showed you how to do that. Then how did you apply it here? This, of course, you need to be very procedural. But then we were able to calculate the final answer. And I hope I was also able to show you a physical interpretation of that answer. That's probably the most important thing to take away here. And the final resultant moment is also physically described here, although it's very difficult to see from this point of view. All right, I encourage you to really go ahead and perform the calculation for this part of the problem, where you have to form an r vector from this location of the pipe to this location of the pipe. So that means your r vector will change, your f vector will remain the same. And the reason I want you to go through that is because you will see that some numbers in that r vector have a pleasant implication on this part of your calculation, and you can quickly make some conclusions about which I, j, k component is affected by changing some of these numbers in here. So I really recommend that you do that. I wish you good luck with that. And for me, it's time to move on to the next problem. All right, now it's time to look at a little bit more complex problem, and more complex is really not more difficult in this case. All we have to deal with is with two forces. Here we have F1 and here we have F2. And now you need to calculate the moment that is acting at the origin of the coordinate system due to those two forces. So what do I need to do? You remember this from some previous lectures, that the moment is really nothing equal than F times D perpendicular, but also when we had multiple forces, it was the summation of that. And so in other words, we can just say that the summation of R cross F is applicable as well. So this is M vector. So what I have to do is I just have to find the moment due to this force times its distance, and then the moment this force times its distance, and we are good to go after we summed them up. So what do I have to do? Geometrically here, I just bring in two vectors. I bring in my vector, let's call this here R1. So this is R1. And then I also have a vector R2. Let's draw that here. And once I have those described, I'm kind of good to go, because lucky for me, all these problems are already given in IJK form. So let's go ahead and move through the problem. So my R1 is really nothing else than in the negative 1.5 I direction, and in the y direction it's plus 2, and in the z direction it's plus 1. And that is already the full description of my R1. This happens to be in meters in this problem. My R2, on the other hand, is equal to 0 I hat. That will make my life very easy. Plus 2 j hat and plus 1 k hat. And hopefully you could follow that. I don't think at this stage in the lecture it's really important to still describe this. We have gone through many examples on how to read these 3D pictures. So, but you have it in the video, so you can pause if you want to, but I will move on now in interest of your time. So what do I have to do now? I have to write down these two vectors with their corresponding forces. So if I want to do that, I would say that my M about O is really equal to the summation of R cross F. And so therefore I would end up with two matrices. I would have matrix 1i, j, k. And let's start with our R1. So minus 1.5 plus 2 and plus 1. And then I match that with F1, which was nothing else than minus 300 plus 150 and plus 200. And that would be my first matrix that I have to find the determinant of. So let's copy I, j, and minus 1.5 and 2, minus 300 and plus 150. And that is the first part. So now I have to add my second determinant, which of course also has I, j, and k components. And I now have to use my second lever arm, which is 2 and 1. And my force now is really nice. It's 0 I hat, 0 j hat, and minus 450 k hat. Last but not least, I need to bring in my I hat, j hat. Down here I have 0, 0, and then I have 0 and 2. And I won't even show you how to do all the diagonals, especially not here in the first one. That is similar to what we've done before. I just want to point something out about this diagonal. Now that we completed the summation, I just want to mention that you can see how nice and easy these problems can be, even if they look difficult to begin with, because if I draw my diagonals, I have the positive one here, I have the positive one here, and the last positive here, and then I have the negative ones, which are here, here, and here. And let's do the diagonals. The positive ones are first. So minus 450 times 2 is what? Plus 900 here really. So plus negative 900, I should say. And then now the fun starts. This is 0, this is 0. I don't have to worry about this. This is 0, this is 0, and this is also 0. So you see how easy that can work out. And why is that? That is simply because the 450 is acting downwards parallel to the z-axis and on top of the y-axis, right? So therefore, you only have really an I component. So this force really rotates only about the x-axis, because this force in the z direction times its distance in the y direction. So zy gives you an x component. And there's really nothing else that you can cross this with, so that you only find a moment about the x-axis. And like I said, this is very simple. This is like it was before. So I will only give you the final answer to this. And you will find that your ultimate moment now, the numerical answer to this, is nothing else than equal to minus 650 I hat plus 0 j hat actually, and 375 k hat. And that is something you should be able to calculate, and I really encourage you to do that and to try to arrive at that answer. And let me double underline it. And of course, the rest is, as always, the moment magnitude would come out to be equal to 750.4 Newton meter. And then you have the angles, and I will just give those to you as well. Alpha is equal to 150. Beta is equal to 90 because of the 0, right? And gamma is equal to 60.1. And again, I encourage you to come up with these numbers and to actually verify them so that you are well prepared for your upcoming exam. This is an answer, and this is an answer as well. And that technically concludes the problem. I mean, I did not show you all the details on how to solve this, but at some point we would just turn in circles. You already know how to do that. You also now understand how a 0 affects your calculations. And I believe now you have all the tools you need to solve moments in three-dimensional structures. So that ends our lecture, and it's time for us now to move on to our concluding page and summarize our learning experience and take a look at the upcoming homework.